Hello, welcome to my channel Code Design. Today I will be discussing one object-oriented system, designing an LRU cache, least recently used cache. And for this design, we'll be taking the problem statement from Leetcode because Leetcode has this problem in place. So let's try this. Um, so this design a data structure that follows the constraints of a least recently used LRU cache, and LRU cache will have a constructor LRU cache given capacity, um, the capacity of the cache, and there will be a get method and there will be a put method. So we have here LRU cache get and put, and the constraint is here, the function of get and put must each run in O1 average time complexity. That means you cannot look through your data structure to get a element, to delete it, or to move it from one place to another. So if we look at the example here, we can go through it to understand how it should work. So we need a list. So cache, say we use a linked list here for cache, a queue, and we use a hash map here to store the key value pair. So 1 1, our cache, 1 will be there in our cache, 1 will be there in the hash map, key 1, value 1. And then we have 2 2, so we add 2 in the cache, we add 2 in the map, and value is 2. Then there is a query for get1. Get1 will return 1 because it is in the hash map, and it will move 1 from here to at the end of the list. Because 1 is used, 1 is frequent, we want to put it at the end of the list, because eviction or removal we are doing from the beginning of the list. So we want the things that we want to stay longer in the system, in the cache, we put it at the end of the list. Now let's see 3. We have now 3. We add 3 in the map, key 3 and value 3. So key 3 and value 3, and we add 3 here. But now our capacity is 2 and we have now 3 elements, so we have to evict 2 from here. We need to delete 2 from here, delete 2 from the hash map, and the next call is get 2. So no 2 in the hash map, so it will also in the cache, so it will return -1, which is expected. And then we have 4. Let's add 4 in the cache, in the hash map as well, for 4. And now again we have 3 elements, and our capacity is 2, so we have to get remove of 1. We need to get remove of 1 in the cache and also in the hash map. So we have now 3 and 4, and then when there is a call of get 1, it will return -1 because it's not found. And then get 3 will return 3, it's in the map, but what it will do, it will put 3 from, take 3 from here and put it in the last, like this. And we can delete 3 here, and the next call is 4, so 4 is there. So again, we have to do this. 4 will come in the last here, and we need to delete 4 here. So now I think we got a basic understanding how the cache should work internally, and there is more constraint here. Our capacity of cache would be 3000. Key value of key would be 10,000. Val Value would be so range of key 0 to 10,000 and value 0 to 100,000, and there will be at most 200,000 calls to get and put. So let's go to the IntelliJ. That would be easier to show the code. So this is my code of the LRU cache. So this is the hash map. We have cache map, and instead of creating the concrete double linked list here, we can also pass it from outside. So the driver class that will be calling this, creating object of this LRU cache and calling it, we can pass the double linked list as D2 interface, because we are using a interface here. This is not mandatory, but good for design. So we have actually our node class, which is the key value, and these are integer, and we have the next and previous. Next will point to the next element, and previous will point to the previous element in the list. And the linked list will be implementing DQ interface. So it will have add last, remove first, remove, and these methods, and our cache. So we are doing here method constructor overloading, because this is what we have on the capacity in Leetcode. But if we want to do like this, then we can actually do a constructor overloading and call this constructor from here and pass the linked list object here for Leetcode. But for other code, if we want to use this independently, we can create a object of LRU crash with capacity and any kind of data structure. It could be a linked hash map or a different implementation of linked list or queue. But it has to implement the interface MyDQ in order to pass it from here. So let's see the method get and put. So the get, when it is called in the hash map, is try to find if the key exists. If it doesn't exist, it's return -1. If it exists, it gets the node and move it to last. So what is moves to last? It actually remove the node from the queue where it is and add it in the last of the queue. And so this is our get method, and it returns the value of the node get. Now we have put. So put we have two sections. One is update and one is add. So update is this first option, that if the hash map contains key, that means we already have it. It gets the node and it updates value for the node, and again move the node to last. So move last. And this section is for new nodes. So it's not in the list, it's not in the map, so we need create a new node, and then we put in the hash map by key, and we add it at the end of the list. Now that we add it in the end of the list, we check the size of the queue and the capacity. If the size is greater than capacity, then we do the eviction, cache eviction here. We remove the first element from the queue and add it, no, remove the first element from the queue, and we remove the element from the hash map as well. Because if the element is not in our queue, doesn't make sense to keep in the hash map, and it will be error prone. So now we can actually go and see the W linked list. What we have here, there is add last. So add last, say we have one and two already in the list, and we want to add three. So in order to do that, we need to find the last element, right? Whatever is our last element in the list, which is currently two. So we keep the last element reference, which is two, and then the node 3 will be adding, and will be adding at the last. That means it will not point to any node. So we set node dot next to null. So next node of 3 would be null. And we say now last is node. That means 3 would be our last node. Now what if the previous node is null? That means we didn't have anything in the list. Only 3 is the first element. Then what will happen? Um, 3, if 3 is the first element, then first would be node. Else, if 3 is not the first element, that means if there are some element before 3, then whatever element we had 2, 2 dot next would be 3, and 3 would, previous of 3 will point to 2. So this is a good thing to remember, because I had a test case failure for this, because I forgot to link back the last node to the previous node of last node, and we increment the size. And then remove first. What we do is remove first. To remove first, we need to actually get the first node, um, to so that we can return. Say we have 1 and 2, so our first node is 1, and if we remove this first, what will be the first node? This 2, right? So which is basically node dot next. So we assign first equals f dot next. F was 1, now f would be 2. And if first equals null, when first equals null, that means we did not have anything. We are um, yes, if our yes, if there was empty, then last will be null, and otherwise will be first dot previous equals null. So whatever node we remove, we remove 1, and we have 2 now. So 2 is our first, current first. So first dot previous, that means 2 dot previous would be null if there was no element here. No. So now that I remove 2 1, so 2 is our first element. So first element, these 2 dot previous will be null. And let's go to the last one, remove. For remove, what we need to do? Say we have here 1 2 3, and we want to remove 2. So if we want to remove 2, we need to get the previous node of 2, which is 1, and we need to get the next node of 2, which is 3, and if previous not equals null. So in this case, our previous is not null, so previous dot next, that means 1 dot next would be node dot next would be 3, because we are removing 2. And the same thing, if next not equals null, in our case is not null, so next dot previous, that means 3 dot previous would be previous, that means 1. So 3 will point to 1, because we are removing 2. Now if node equals last, that means if we want to remove these 3, then our last node will point to node dot previous, that means this node. And again, if node equals first, that means if we want to remove this node, Then we are removing this node, so our new first will be node.next. That means our new first will be 2, and we decrease the size here. So we have isEmpty, which is basically check if size equals 0, and we have the method to return size. So now that I think I have gone through everything, what we can do, we can get this code, and we can switch back to browser, and we can see what happened with this code. Remove the package and run it. Okay, so it passed the simple test case. Actually, it will also pass the all the test cases because I have run it the same code today. It was succeeded, and it took 45 millisecond for as a runtime, and it beat 69.30%, and the memory was this 113.34, and it beat 61.98%. So however, I had another, so I tried so many ways to solve this. One of them was using a linked hashset, which is obviously the way when you have less time to implement. I will go through it. So another one was again linked list, but it was maintaining a head and tail node, dummy node, head and tail. So however, let's go back and see another implementation quick. So this is another implementation, so you don't if you have less time like 15 to 20 minutes, then you need to do this, so you can implement it by using a linked hashset. So in why linked hashset, because we have to remove in one times. That means provided the node, we have to remove the node. That means the next node and previous node, right? So if we have 1, 2, and 3, and if 2 has been given, so what we need to do, we need to point 1 to 3 and point 3 to 2. Sorry, point 3 to 1. So that means it will be like this: 1 will point 3 and 3 will point back 1. So that's why we have to use a linked hashset, not a regular hashset, because hashset will not maintain the order, and linked hashset will maintain the order. And I have verified the code of the linked hashset. It actually does remove by node by working with the previous and next pointers. So it is O1, and we can still use the same way the hash map that we are using, and the code will be like this. So it's much smaller code. So I will be providing the link of this code of my website in the comment, and I think that's it. So let me know if how it goes, and the sound quality and everything, because this is my first video. Bye.